So let's start. And my pleasure to give the floor to Mr. Josh from Atkins. And he has been involved in a wide range of projects and has supported the energy storage program for DEC, the UK Department for Energy and Climate Change. So we are very much looking forward to listen to you. So you will be one of the presenters in this section dedicated to engineering solutions. Please, the floor is yours.
Thank you, Paula, and good afternoon, ladies and gentlemen. My name is Duncan Josh, and I work for Atkins, the engineering consultancy firm. And today I'll be looking at some of the measures that one of the European member states has been undertaking to accelerate the deployment of energy storage systems. So the UK's Department of Energy and Climate Change, also known as DEC, initiated their storage programme in October 2012, just over 3 years ago, and this was primarily to promote the development and deployment of new energy storage solutions. It was an open competition and it received a diverse range of applications. It was split across two main streams. First of all, component research and then also demonstration. By component research, this sought to support components or aspects of overall energy storage systems, but not the full systems. There were also a number of energy storage-related studies conducted within this stream. This included looking at new opportunities for pumped hydro storage in the UK, looking at the safety aspects of using hydrogen in a residential setting, and also compiling a best practice guide on electrical energy storage. The demonstration stream sought to support the development and subsequent deployment of complete energy storage systems. And we were awarded the role as technical advisor and have been supporting DEC throughout the programme. This started with the initial project assessment and selection phase, and now continues to the project monitoring of the supported projects. And it's the 4 demonstration projects that I'll be providing an overview for next. So first we have Moixa. They've developed a residential energy storage system complete with an aggregated control. Then there's REDT. They developed vanadium flow battery system, in this instance in the support of existing wind generation. Then there's Highview, who have developed a liquid air energy storage system. This one is integrated with a waste management facility operated by Viridor. And then finally there's the Everest Consortium, who have developed electric vehicle rapid charging stations, and these utilize second life lithium-ion batteries. So firstly, Moixa. They've developed their units that they call Maslow. They're around 2 to 3 kilowatt hours in capacity, and they have an integrated inverter in, and they can also act as an isolated DC supply. This is one of the units installed, similar in look and appearance to a small wall-hung hot water heater. One of the prime markets for this storage technology is to support local PV generation. This is a typical UK demand profile, and this is the solar generation profile. A lot of this energy would normally have to be exported or just wasted, so the storage system allows it to be utilised to meet the evening peak demand. In a similar way, the system can also utilise cheap off-peak electricity to deliver it to this demand period as well. This is the system deployed in a university campus. It includes a low-voltage DC network supplying LED low-voltage lighting, also power for laptops and charging of USB devices. So the second aspect of this project was to actually build a centralized control and aggregation platform. This allows multiple supplies and demands and storage units all to be integrated. By combining or aggregating many smaller storage units that are held at the residential level, these can then be aggregated, controlled as though they're one larger storage unit, which allows them to be able to offer services to the grid operators, which in the UK at any rate would normally be restricted to capacities above 1 megawatt. They can also integrate with additional energy storage facilities, and they're now trialling connection with two-way charging with EVs, with electric vehicles. During the demonstration project, Moixa deployed around 250 of these units in different properties and at universities, and then built and integrated them with the central control system. Next, we have the REDT with their flow battery development. So the flow battery is a containerized solution, uses vanadium. It's around 105 kilowatts in power with around 11 hours storage at its full rated capacity. It has independent power and energy components. Liquid electrolyte is stored in tanks to hold the energy, and the central unit, called a stack, provides the power. It's similar in concept to a fuel tank on a car and a fuel engine. This is a close-up of the stack, where 40 cells are combined in series to produce an output of 48 volts. The electrolyte is pumped through each cell. The electrolyte is separated, the positive and negative electrolyte is separated by a membrane, and then there's electrodes between each component. This is the early prototype of the stack in development. These are now being manufactured at larger scale at a dedicated manufacturing plant in Scotland. In addition to developing the energy storage system, the overall objective of the demonstration project was to support existing wind generation on a remote Scottish island. Now, the island is already connected by a subsea cable to the mainland, but this has a constraint on it, and when all the turbines are generating their full capacity, their generation output is greater than that of the subsea cable. So the newest wind turbine has to be constrained, effectively wasting potential energy. The storage system will be used to absorb this energy in periods of high wind production, and then to be able to release it back to the islanders when the wind power generation is at lower levels. This is the finished containerized solution, with the liquid electrolyte being stored at the base of the unit. In the top, you have the stacks and the power electronics. There'll be 7 of these battery units deployed in the full system, complete with a service module here. That will also contain the power control system and the medium and low voltage switchgear. Next, we have HighView, who have developed a liquid air energy storage system. And their liquid air energy storage system uses cryogenically cooled liquid air or nitrogen to provide the storage medium. It's a scale-up, around 5 megawatts in capacity, 12 megawatt hours of energy, so roughly 2.5 hours at full rated discharge. Again, it has independent power and energy components. It utilizes mainly existing industrial equipment with some minor modifications, and has the potential to be rolled out for large-scale grid-based storage. And at this scale, it has a high energy density. This is the liquid air energy storage energy density against compressed air, pumped hydro, and vanadium flow batteries at the end. These are the 3 stages of the cycle. First being the charge, which uses a standard industrial air liquefier to produce the liquid air. This is then stored cryogenically in tanks at low pressure. And then to recover the energy, the discharge phase pumps the liquid air up to a high pressure. It's then evaporated and heated. At this stage, waste heat from existing processes can be injected into the system to improve the performance of the overall system. The high pressure resulting gas is then used to drive a turbine to generate electricity. This is a CAD view of the finished plant being deployed on an existing waste management landfill site, which is operated by Viridor. These are the cryogenic storage tanks, around 20 meters in height. This is the turbine and generator enclosure. Here we have the existing landfill gas engines. These have been using the landfill gas that's already generated on the site to produce power, and these now have thermal recovery units fitted onto them. The thermal energy is recovered as hot water. It's also stored in these new thermal recovery tanks here, thermal storage tanks. And then this energy is then used during discharge to improve the overall system performance. It's applied by the heat exchangers during the discharge here and at the expansion evaporation stage. And lastly, we have the Everest Consortium, who have developed rapid charging stations for electric vehicles utilizing second life batteries from electric vehicles. So the demonstration project was also integrated with solar PV and a wind turbine. This was to provide just proof of concept for a standalone charge station. It's around 250 kilowatts of power and around 1 hour of discharge at its full rated capacity. It's primarily designed to help to alleviate distribution constraints. For instance, when you start rapid charging EVs, typical power requirement might be 40 to 50 kilowatts. If you start putting a lot of rapid charge units in a fairly constrained area, you're imposing a large load onto the grid. When you're imposing that, the existing distribution system might not be able to cope. With a system like this, you can then spread some of that impact out and help to control it. It utilizes second life lithium-ion batteries that have already had their primary life within an electric vehicle. So one of the key objectives was actually to prove the viability of using these batteries, so when they're no longer fit for purpose effectively in an electric vehicle, what use can they have subsequently. And in addition to producing the rapid charging solution, the aim of the project was also to demonstrate wider applications. This is the original containerized solution, which included a guest suite. This is where different battery suppliers could bring their second life batteries for test purposes. So a key element of the system is to provide control over lots of different battery units which might have different characteristics and have different states of charge and have different performance characteristics. So the optimization of the central control system was a critical aspect. There was a lot of different testing done of the second life batteries, and then the system was redesigned for commercialization. The batteries would typically have 75 to 80% of their original capacity when they're moved out from their original purpose from the EVs. The system uses the complete battery packs, so rather than dismantling them using the individual cells, the complete battery packs are utilized. This means that the functionality of the battery management system can be used, which is then plugged in and controlled to the overall optimization system. So in summary, energy storage has many shapes and scales and should be appropriately matched to the services that it's expected to provide. The control and integration of storage systems is as important as the underlying storage technology. And where possible, the reuse of existing mass market or industrial products provides tangible cost and performance benefits. And finally, taking a whole system approach can provide further significant benefits. Thank you.
Thank you very much, Mr. Jost, for this very interesting presentation on the lessons learned from a series of projects that are part of TEC Energy Storage Program. Now, I'd like to move forward and give the floor to Mr. Ralph Grether, who is here to talk to us about hydropower as one of the large energy storage providers. Mr. Grether is head of the program management, patent and innovation at VOI. The floor is yours. Thank you.
Thank you, Chairman. Dear ladies and gentlemen, thank you for the opportunity to discuss today afternoon with you the hydropower technology as storage in our electronic grid. For those of you who do not know my company, Voith or Voith Hydro, please allow me a short introduction. Voith is a family-owned company with headquarters in Germany and factory branches offices all over the world. We will celebrate our 150th anniversary next year. Voith Hydro is one out of 4 divisions and is providing complete electromechanical equipment and services for all sizes of hydropower plants worldwide, new and modernization business. Voith Hydro is member of the Hydro Equipment Association, HEA, with a clear vision to position hydro as the first, largest, and most efficient renewable energy source, which also fulfills other important needs like CO2 savings and what we talk today here, the energy storage. The breakdown of my presentation will be as follows. We will discuss some general topics, followed by 2 examples of pump hydro plants, and we will wrap up with a conclusion. We will learn about the motivation to have storage at the grid, but now we start first with the parameters important to compare storage technologies. Storage on the transmission grid exists since decades, and some of the storage technologies are also available since long. What we see from the investigation is that hydropower is the prevailing technology when it comes to large-scale storage needs. One reason for that is for sure the high efficiency that can be reached, and in the same way, the cost effectiveness this solution can provide. What we see is that the largest storage applications are with hydropower, an extremely durable technology with more than 50,000 total cycles. Known since years, some of the storage technologies have not reached the commercial operation zone yet. They are still on R&D and demonstration levels. The takeaway from this first chapter is we need to remember the 4 parameters to compare storage solutions. This is power, capacity, cycles, and efficiency. By this headline, you may ask yourself, why do they need development with hundreds of applications running in the field? The task of the storage application installed some years ago was to take up power from fossil and nuclear in the evening when the workers in the factory went home, and the storage was unloaded in the morning when the workers came back to work. In the future, we see a huge increase in all storage products from seconds to years. In almost all countries, we will have in the future a remarkable number of wind and solar installed. Sometimes wind is not blowing and sun is not shining. But we will have minutes, hours, and seconds where we have a much more production than we can use. This unpredictable, fast changeover is one of the new challenges, beside others, we described as R&D needs for pumped storage in the HEA roadmaps. In the example of the pump storage plant Frades 2 in Portugal, we can have a look to some slides presented by the owner, the utility EDP, on their motivation to build these plants to be finalized in 2016. EDP faced an enormous wind power capacity increase in Portugal grid. With the high volatility in production, the market prices became unpredictable. At the same time, the grid stability, the security of supply, the reactive power to enable energy transport needs to be provided within seconds. Supported by the national policy to back up wind with storage, EDP decides to build a new pump storage plant with the electrical power of 840 megavolt ampere. It was estimated that this plant will have 1,038 gigawatt hours, which is compared to a 5 megawatt windmill with 20% full load hours per year. Then you can have 120 full windmills operated 1 year, and you can store everything here and reload it from this plant. But the EDP not only decided to build a large storage to provide negative and positive control, EDP ordered the new speed variable technology to be prepared for future needs on flexibility in taking up energy from the grid. The second example, the requirements from the grid are changing. The possible business model, renewable energy providers do see a chance with hybrid plants in case here an intelligent combination of wind and pump storage plant. You see the 4 wind locations over there and the pump storage reservoir down there. The really innovative thing here, what we have in this plant, is that the fundament structure of the wind power is used as upper reservoir for the pumped hydro. The solution provides predictable green energy. They can store these 70 megawatt hours in this fundament of the windmills, and so they can bridge 3 hours totally without wind. Now, let's wrap up. We together have the target to reduce CO2 in electricity production. We need to manage the volatility that comes with renewable, like wind and solar. We have to cope with a decoupled demand and response, and at the same time ensuring the security of supply. A solution is available to help with these challenges. This is storage and hydropower as energy storage. Thank you very much for your attention. I'm open to your questions. If I cannot answer them all here, you see my phone number and my email address. Thank you very much.
Thank you very much for your presentation. And our next speaker is Mrs. Anna Carolina Tortora, and she's heading the Department for Innovation and Development at Terna. So she will give us here the perspective of a TSO, transmission system operator. The floor is yours.
Good evening, everyone. So I'm going to start by explaining to you who and what Terna is, what it does, why we reverted to energy storage, and give you some background as to our projects. So what is Terna? Terna is the Italian transmission system operator. We are a regulated utility. We are in the stock market, traded on the stock market in Milan since 2007 with a market cap of about 8.7 billion. We handle 310 terawatt hours, I think, as of last year, of energy each year. We manage the safety of the grid through 70,000, a bit more than that, kilometers of three-phase conductors. That's 150 kV, 220 kV, and 380 kV, interconnected with the rest of Europe, and with about, I think, 8 distribution centers. I'm sorry, we just changed all the configuration of the grid right now. So why are we here? So first I'm going to give you some background. This is the European background. So back in 2009, every country in Europe published their own objective, renewable objectives. We call this the National Renewable Energy Action Plans. You've heard about them, 20-20-20, reduction of CO2. And these are some of the final goals that were reached. We're talking about, here from the graphs you can see for solar, about 80,000 megawatts of solar in Europe by 2014. Actually, by 2020, we already reached that goal back last year. Wind is also looking to go up very fast this year with the new incentives coming up, and especially we're reaching now grid parity in many of these systems. And this presents a few challenges, as you can imagine. So this is what happens in Italy. So in Italy, in 2008, we had the massive growth of renewable energy. I'm sure you heard about it. One of the main issues that we had compared to Germany and Spain is the shape of Italy. Italy is long and narrow, is a boot. So most of our sunshine and wind are located in the south of the country, whereas most of our industry is in the north, the industrial north. This, for a TSO, is a huge challenge because you interconnect the south to the north, but this means, especially when you have a lot of renewable going on in the south, congestions. Especially in the Apulia region, which it's the boot of Italy, if you think about it that way. We have about 800 megawatts of wind power plants installed. This is almost a nuclear power plant. And the whole installation is within 400 kilometers. So a gust of wind, literally a gust of wind the last 5 minutes, brings to the grid 800 megawatts for 5 minutes, and that just goes away. So we're getting, in those 150 kV backbones right there, we're getting congestion issues. So how did we deal with them? Well, we'll go through it. Mostly, we curtailed it. You've heard about it. You know, we had in 2010 about 500 gigawatt hours of curtailed energy. And that is energy that is paid as a premium because we have a lot of incentives, and they have priority dispatch. Not a very convenient solution. Then we have another problem, which is a power problem. And that is given by the fact that, of course, renewable energy has priority dispatching in Italy because marginal cost is 0, of course, and you already paid for it. So what happens with that? That happens that a lot of our thermal energy is left out of the market balancing. So now you have mostly renewables. You cannot really use reserves with renewables. They don't provide much safety to the grid. So now you have a power problem because you have very low inertia in those islands. And we need to learn how to integrate them properly within the grid. So how do we defend the grid? A lot of people here are familiar with it. This is mostly for those that don't know what a TSO does, what a transmission system operator does. We defend the grid with 3 reserves. Because we're so original, we call them primary, secondary, and tertiary reserve. Then you have inertia, which is pretty much a physical reaction of the system itself. So what inertia does is you have your thermal units on grid. These are rotating units. And imagine all of Europe is rotating at 50 hertz. Every single thermal machine in Europe is going through that. Like a car, when you're trying to brake, if you try to brake that car, it will have its own inertia. It wants to keep on going. Now, most of these thermal power plants will be providing that kind of inertia to react to whatever change you're trying to provide. So that's inertia. And that gives you the time, because those rotating masses will slow down the change so that you can come up with your first line of defense, and that's your primary reserve. Primary reserve in Italy is for the country. It's a free service. Every power plant connected to the grid has to provide 1.5% of their nominal power for my uses. Don't worry, I will call you when I need you, but I need to have that 1.5% free. So primary in Europe, and this is an NSOE regulation, meaning the European Network of TSO regulation, has to be online. Within 15 seconds of being called, you have to give me 50% of your power. Within 30 seconds, 100%. Every year, NSOE decides each country how much they have to provide in primary reserve. So Italy, this year, 400 megawatts. Germany, this year, 600 megawatts, and so on. Everyone has its own quota, because this is everyone helps everyone sort of situation. And primary reserve will stop my change in frequency. Then comes in secondary. Secondary comes in without 240 seconds, and that is a paid service in Italy, in many other countries as well, of course, I think all of them. It's a very actually convenient service to supply. And secondary's job is to restore frequency. So it was primary stop the change, secondary restores it back to 50 hertz. Tertiary regulation, which comes much later, has a job to restore secondary reserve. So that, gentlemen and ladies, these are my 3 reserves. These are my 3 systems. Now, of course, you can imagine in a world made by renewables, this might not be always adequate. So one of the reasons why it's not adequate is because 15 seconds, 30 seconds is just not good enough. It's not good enough. Imagine most of these renewable systems are electronics, so they have inverters. And you have sun and wind, they happen within instants. You get a cloud. So you need something that reacts just as fast on the system. So we started looking at all the different mediums, and of course, hydro pump was one of them, and compressed air systems, and of course, infrastructure development. So one of the issues that we found with many of these is for hydro and compressed air systems is location. These are location dependent. This is a big deal for us. Why? Because if my congestion is in the south of Italy, I cannot have a hydro pump in the Alps. It's just that I don't know what to do with it over there. I already have those. I need one right there. Secondly is timing. Time. This is Europe. We cannot just start building the next day. You have authorization processes. We have NIMBY. NIMBY goes crazy with NIMBY. So imagine infrastructure development. So we started looking into batteries because they were very fast to be deployed. Yes, they were very expensive back then, but today we feel that they were a very good investment. So when we started selecting batteries, we started looking, and a lot of people came to visit us, and there was a lot of different solutions, and we realized that not two were alike. And depending on the type of service that you needed to do with them, you needed to choose a different technology. So these are some of the ideas we have. We started classifying them into power and energy intensive, starting to look at which solution was best for which problem. And again, when it comes to electrochemical solutions, the world out there is crazy with them. Even you say lithium ion, there's not just one type of lithium ion, there's tens of lithium ion. Each one is its own secret recipe, perfect solution for a specific problem. Some of them are good for very hot weather, some of them are good for very cold weather. I swear to you, some guy came to me with a battery that could operate at minus 40 degrees Celsius. I'm from Italy. I don't think I've ever seen that temperature in Italy. But, you know, there is such a thing as well. Again, then you have Zebra solutions. You have supercapacitors, lithium-ion supercapacitor, vanadium. My colleague from the UK spoke about it as well, so a lot of them. So, you know, we took it slowly. We started thinking, okay, how do you start thinking about this problem? First, you understand what kind of problem you have. You have to study the problem and bring it down to the basic terms of it. So find out exactly what you need, because it was an expensive solution to buy, and we were not used to buying this kind of solution. So if we're gonna spend the money, you better be sure of what you're doing. So we classify the problems into two main groups: an energy problem, south of Italy, congestion problem, power problem in the islands, so loss of inertia and needing to have regulation boost. From there, we started looking at what kind of usage we started to make of it. So are you gonna use it a lot? Are you gonna use it very little? Is it gonna be with very high operational costs and so on? All of this went inside the cauldron of decision-making, and we finally came up with two separate projects. So what we call the grid development plant, energy-intensive project, and the grid defense plan, power-intensive project. So the energy-intensive project was 35 megawatts to be developed in the south of Italy. The solution that we chose is NGK's NAS batteries, sodium-sulfur batteries. You've heard about them. They had the biggest historical data back in 2010. We're talking about 3 substations in Italy that each host about 12 to 10 megawatts of these solutions. They have a ratio of about, for every megawatt, 7.2 hours of storage. These are the hot batteries. You've heard about them. They have a round-trip efficiency, if you're using it regularly, of about 70 to 75%. Again, depends on the usage you make of it. And they have, of course, the same reaction times of any battery storage. So we're getting about 110, 120 millisecond reaction from a signal being sent from our National Control Center room to the battery. That's the kind of reaction we're getting for full nominal power. This is an example of the solutions that we're deploying. So you see on the left is the batteries, the cell itself, which then assembles into a module, which at the same time assembles into a rack, which makes up the battery. So that you see is a 1.2 megawatt battery, and that's one of our stations. Then comes the grid defense plan. So that's I think the princess project that we call it, because here we're testing so many different technologies. So as I said, the problem is a different one. This is a power issue. So we'll start looking into lithium-ion Zebra solutions, and then we start making it into an actual lab. But this is a grid-scale lab. So the lab itself is 16 megawatts. And I know that these don't seem like big numbers, especially after hearing hydro people talk, but we're talking about a total here of about 75 megawatts of energy storage solutions, and that's a huge amount for batteries. It's unheard of in Europe. Well, now it's heard of. Other people are doing more, but when we started, no one had done this much in Europe. So we divided into 2 steps, because the authority for energy and gas in Italy said, I'm not going to give you the money to do 40 megawatts of energy storage solutions if you don't know what the hell you're doing. So you start with the first step, 60 megawatts, try them out, let me see how they work, and then if those work out, move on to the next 24. So these are my 16 megawatts. So I have about 5 types of lithium-ion. I have the French, Saft. I have a couple of Korean, Samsung. Siemens is actually running LG batteries, so that's my second. I've got the Chinese, BYD with their iron phosphate. I've got Toshiba. I got Zebras. I have General Electric and Fiam, the only Italian battery maker in there. And I'm testing now, actually, flow batteries. I'm installing them within this year, and I'm also getting supercaps this year. So each one of these solutions, as you can see, even though they're lithium-ion, a family lithium-ion or a family of Zebra, they all have different performances, different things that you expect. And I am testing them against real services, grid services, to see how they react. Because these are electrochemical systems, so what you're getting is aging that is not exactly what the actual suppliers declared. You have different effects happening. This is your typical lithium-ion solution, what you're getting. You start from a cell, it assembles into a module. Again, it assembles into a rack. That's why they're called batteries, of course. And that itself goes into a battery module. In order to connect to the grid, you need a PCS. The PCS hosts the EMS, the Energy Management System, which is the system that communicates with the control center. And they are also assembled within our own control system, the SCADA system, on site. This is a Zebra. It looks very much like the NAS ones. It's hot as well, but it has some behavior that is different. First of all, you can cool this battery as many times as you like. You cannot do that with NGK's NAS. The efficiency is the same, but the storage time is not exactly the same as NAS. We're getting here about 4 hours compared to the 7.2 hours that you would get with NGK's solution. And these are hot batteries. And they're very safe, actually. They used to, like lithium-ion, these started for cars. This is flow batteries. You saw it before. There's different types. We're testing 2 this year. I think Ronke Power is one, and the other one is the German one. I forgot the name. I'm sorry. I have it written down somewhere. I'll remember later. I'm also getting supercaps, which is on the total separate end of the spectrum for energy storage. And these are some of the pictures. You see, they're real. We're actually building and we're actually using these batteries, and they're working. They're actually working. My Toshiba batteries are reacting with 90 milliseconds. I mean, 90 millisecond reaction. I send a signal, that's my response. Full nominal power. There is nothing on the grid except for maybe like tripping, like you're turning somebody off, that is that fast. It's incredible. So what are our objects? What is our goal? We want to test them. We want to test different services because I want to know exactly how they age. Why? Because nobody's really done this. Nobody's really tested these batteries against specific services. So you want to do frequency regulation? That's how much the battery ages. You want to do load shifting? That's how it ages, compared to the temperature, compared to a certain behavior. So I want to be able to model this in such a way as to come up with an actual formula that gives me the cost of a specific service per technology. Also, I'm learning how to use them in a convenient way, so a business case for them. And the business case depends on how you use them. So I'm combining signals. So there's different ways to integrate these batteries. There are those that are good at peaking. There are those that are good to give you base load, exactly like you would in any other system on the grid. And we're learning how to use them together. Finally, I'm a TSO, of course, but we believe that energy storage can be used for so many different applications. We've seen them being used and theorized for generators, as well as for system operators, and for retail, so also for consumers. How? Well, there's different services that we're trying to test. In the specific case, in Italy, we're starting now the market for demand response. Energy storage is a great backup for that. So it's one of the things that we're definitely looking into. And the reason we're here is because up till this year, Italy was the #1 for energy storage, electrochemical energy storage, which is why when the Germans started developing, we had a lot of our own integrators. So NIDEC, for example, which is Exxon-Saldo Energia, won that tender with LG batteries, but they're supplying them. Why? Because they're getting so much know-how from our projects. And that's my presentation.
Thank you very much. And to complete our panel, please, we have the last speaker, Mr. Frank Verschagen, is from Deme Group, project director, and is talking to us about energy storage in the GCC, so an interesting presentation as well, some solution coming from Europe. Please, the floor is yours. If you can, 10 minutes.
10 minutes?
Yeah.
Okay. Thank you, Mrs. Chairman. So the project and concept I'm going to introduce to you today is called E-Island. The E stands for energy and energy storage, but also for environment, as will become clear in the presentation, I hope. So it's a concept of offshore pumped hydro storage. And what you can see here is a picture of the Belgian coastline, with on the right-hand side a harbor, the harbor of Zeebrugge, and here on the left-hand side you can see an animation of the island that is currently being developed. It is important to say that this concept was initiated by the Belgian government In 2014, the legal framework was developed for that. And also, the European Commission has adopted this project as a candidate on the list of PCIs, projects of common interest. First of all, the story of renewable energy is, of course, clear to you all. As you can see here, offshore wind and PV, these are the two sources that we mainly use in Belgium. We all know these sources are intermittent, and that, of course, we need storage in order to cope with this intermittency. If we're talking about energy storage, we are now talking about large-scale energy storage, and as we all know, there are only two mature technologies right now for this, and it is pumped hydro storage on the left-hand side, and on the right-hand side, you have the compressed air energy storage. The pumped hydro accounts for about 98, or I saw 99% of all the large-scale energy storage worldwide. It has, however, also some disadvantages. It has important onshore spatial constraints. It is also quite difficult to get it permitted. And also water scarcity is an issue, certainly in countries, for instance, like around the Arabian Gulf. The other option you have is the compressed air energy storage. It is also mature, but only 2 stations have been built since 1978. So in the last 40 years, only 2 developments were made. And this is mainly due to unfavorable soil conditions. You need very, very specific soil conditions. You need cavities in the ground where you can compress the air into. So, as I said, there are spatial constraints onshore. So the solution we want to propose is energy storage at sea. The principle is shown in this slide. So on top, you can see the principle when there is, I would say, too much electricity in the system. You can pump the water out from a reservoir at sea, and you pump it towards the sea. So what you can see in the middle is a reservoir that has been dredged into the bottom of the sea, and all the material, the sand, we should say, that came out of the bottom of the sea was put around the pit you have made. So you create a kind of atoll. At the bottom of the slide, you can see it in the reverse mode, namely in the turbine mode. So we are now generating electricity by letting the water of the sea flow back into the reservoir. This is basically how it works, so it's a kind of inverse pumped hydro. On the right-hand side, you have an impression of the turbines that are being used. So this is a typical, I would say, low-head application, which has also certain advantages due to the choice of the turbines you can make. At the bottom, you can see an animation of the project, where you see the reservoir itself, the dimensions. Just to give you an idea, dimensions are 2.8 kilometers in the large axle, and the short axis is about 1.2 kilometers. And it is surrounded by beaches with about 700 or 800 meters large. This is an example of a conceptual design that is currently being developed for the Belgian case. I already gave you some of the dimensions. Just another dimension I have not mentioned yet is the depth of the reservoir is about 30 to 35 meters, meaning you will get a head of 20, 25 to 30 meters. For this conceptual design, for this example, the dimensioning electrically was set on 2,200 megawatt hours, so 2.2 gigawatt hours, and about 550 megawatts, giving you a 4 hours of autonomy, which is sufficient, for instance, to cover the evening peak. This is another example just to show you that artificial islands for energy are not something new. It has already been done by the company DEME. This is a company of an oil drilling artificial island, 120 kilometers out of the coast in the Arabian Gulf. It is called Satah al-Rasbut, and as I said, it's used for oil drilling, but directional oil drilling. It gives you all the advantages of drilling on land, but nevertheless, you are extracting oil from the sea bottom. So this technology, of course, there are also some risks involved. First of all, you have a technological risk, which is tackled by the experience of the company dealing with this development, namely DEME. On the other hand, pumped hydro at sea is also not really, I would say, new. There is, for instance, in France, experience with a tidal farm in La Rance, where pump turbines have already been used for more than 40 years with seawater. For the environmental and location issue, this is always a very important issue to be dealt with, and this is analyzed in a feasibility study that we are making right now. The financial risks, of course, have to be covered and assessed case by case. At the beginning, I told you something about the environmental potential too. So this island, it's not only fit for, you can put, I would say, windmills on it, you can put PV on it, you can put floating PV in the reservoir, so you can use it for renewable energy production. Of course, also for energy storage, what I explained. However, it has also important environmental potential. First of all, it can be a harbor, a safe haven for endangered species. An example in Belgium, the astern is a bird that is endangered worldwide. It has already been studied by a company specialized in environmental studies that this would be the ideal place for the astern in order to nest. As there is also a perimeter of 500 meters around the island, so it is also the ideal place for fish breeding. This is a nature aspect, but there is also a very important economic aspect to this nature development. For instance, right now, people are already thinking and studying the possibilities of having fish farming in the reservoir. On the other hand, in the perimeter around the island, we already know that in offshore wind farms, the fish there is a much higher density of fish within the offshore wind farms, simply because fisher boats are not allowed to enter. This will be the same with this island, and as I was already measured, there is a very important spillover of fish from the safe zone to the sea where they can be fished. I think this was my last slide. Thank you very much, and if any questions, we are available. Thank you.
Thank you very much. Thank you very much for this very interesting presentation on the E-Island project being conducted in Belgium that has potential of interest in this region where we are at the moment. I would suggest the following, given that we are already quite late in our program, to call the last speaker, who was going to be the conclusion, let's say, on stage, and then we leave the question and answer to the end. So like this, we group the 5 presentations. So if you allow me, I would like to invite Mr. Paul Gardner to join us, and he will present to us this World Energy Council report on energy storage. Thank you very much.
Thank you. Can we have the slide? Thank you. It's a pleasure to be here. It's a bit of an honor, actually, because I'm presenting the work of a large number of people, staff within the World Energy Council, but also staff within PwC, who did a lot of the costing work that I'll be talking about, and staff within my own organization, DNV GL. So, what we're talking about here is work that the World Energy Council has created, has brought together to produce a report on the costs and the values of energy storage. We heard a lot this afternoon about costs of the various options, and this report attempts to bring that together, not just to look at cost of the storage device on its own, but cost in particular applications, and also something about value. And this is all to do with energy storage for renewables, principally photovoltaics, and wind. So I'm going to talk about the purpose of the study, the cost modeling we've done by PwC, and some of the results for the application cases, and then we'll summarize with some of the key messages, the implications. But first of all, a little bit about World Energy Council. Some of you will know a lot about WEC. It's basically an organization for leaders in the energy field worldwide. Been going for a long time now, since 1923, and its purpose is to fund this kind of work, other work in areas where there's a general feeling that some greater understanding is needed. So this report that is being launched today on the left-hand side will then be used as input to more reports by World Energy Council, particularly the World Energy Resources report that is due out later this year. If you need to know any more about World Energy Council, I recommend you have a look at the website. Okay, so the purpose of this work was to look at energy storage specifically for renewables, PV and wind. Why? Well, two reasons. The falling cost of renewables, particularly PV, has meant that in many regions, we're finding that the projections for the growth of renewables are being advanced quite rapidly. And therefore, the point at which the integration issues become important, the integration issues of variable renewables into electricity grids, the point at which that becomes important is approaching more rapidly than perhaps was expected. And people are starting to think, what are the solutions? What solutions do I have? And we've heard quite a few of the discussions earlier this afternoon have been on these kind of issues. What do we do to cope with renewables? So that's one of the factors that prompted this work. The other is the falling cost of storage, particularly batteries, which has meant that there's a buzz around about storage for many reasons, but particularly when it's considered in conjunction with the renewables, wind and PV. So what we're trying to do here is to understand the costs of storage in these applications with renewables and also think a bit about the value. Now, this is just a slide to show the potential for cost reduction. Both these lines on these graphs here are for lithium-ion batteries for different applications. The source of this data is from various sources, including Bloomberg's, and it seems to show a very nice straight-line cost reduction as volume increases. However, I have to point out to you, those of you who've got some background in statistics and data analysis, that both the axes on this graph are both logarithmic, and to be honest, almost anything comes out in a straight line if you put logarithmic axes on it. However, the important point is the trend is downwards, and it's quite steep. This slide is just to show you the range of technologies that we considered. You've seen slides like this earlier, in several presentations earlier this afternoon. We're considering everything from supercapacitors at the bottom left through to power-to-gas storage options on the top right. And this is a conventional display of discharge time against energy capacity. So, a large part of this work was cost modeling carried out by PwC. And it's been based upon information that PwC had internally from their own commercial activities, literature review, and also a review by the Knowledge Network on Energy Storage, which is run by World Energy Council. That's provided inputs and review and particularly peer review by people who are actually involved in energy storage projects. We developed two key metrics for cost. Specific investment cost, that's basically CapEx. It's more or less CapEx, the upfront cost of buying an energy storage option. And slightly more complicated, the levelized cost of storage. Now, levelized cost of energy is a concept that's very well understood in electricity generation. LCOS is effectively the same, but for storage. So it takes into account the capital costs, the ongoing annual costs, variable and fixed, and also takes into account a discount rate to produce a levelized cost of storage. So that is the cost for each unit of electricity that is produced by the store. And we produced results for current prices, 2015, actually more like 2014 prices, and also estimates of the effects of forecast cost reductions to 2030. And this is just one example of the results. This is the example for storage in conjunction with solar. So we used two basic application cases, one with solar and the other with wind. And these application cases are absolutely critical to understanding the results. So for PV, we assumed a daily cycle, which is quite sensible. We assumed that the store was charged up during the day and then was discharged for a period of 6 hours later on, probably most likely in the evening. And just look at the blue bars, ignore the orange bars for the moment. The blue bars are 2015. And this shows you quite significant cost ranges. Along the bottom are all the different technologies we looked at. On the left-hand side, PSP, that's pumped storage. And far on the right-hand side is power to gas. And you can see that, for example, the third bar in is lithium-ion. And you can see costs around about 600 euros per megawatt hour from these results. So that's every megawatt hour that comes out of your storage device needs to be recompensed by about 600 euros in order to achieve a reasonable rate of return on the investment. And that's quite high. In fact, it's very high compared to the cost of storage at, of the order of 200 euros per megawatt hour. However, if you look at the orange bars, that's the forecast for 2030. So one of the outcomes of this study is showing that, particularly for batteries, that's the third, fourth, fifth, and sixth technologies there, very significant cost reductions forecast to bring them down well below 200, in fact, in some cases, well below 100 euros per megawatt hour. Now, I must stress again, these cost figures only make sense when considered against this application case. If we change the assumptions about the usage, these costs would change quite markedly. Here is the equivalent result for wind. For the wind application case, we couldn't assume a daily cycle. That makes less sense for wind. So we assumed a 2-day cycle. So basically, 24 hours charging up, 24 hours discharging. Now, for Northern European applications, that's probably quite optimistic. The weather cycle for wind in Northern and Western Europe is around about 3 days. So perhaps a 3-day cycle would be more appropriate for Northern Europe. But anyway, the application case is well-defined and it's rigorously applied here. And you can see these axes are all the same. The axes haven't changed at all since the last one. But you can see that wind storage applied to the wind case is significantly more expensive. And it's all down to this application case, the fact that you're using it every 2 days rather than using it once a day. However, we also see quite substantial cost reductions, particularly for the batteries, through to 2030. So, conclusions from this, these last two graphs are that substantial cost reductions are expected to get us down to values that are attractive, particularly for batteries, and also PV, storage with PV is substantially more attractive than storage with wind for these application cases. So, some key messages we want to get across from the results of this study. Oh, I should say that this study is now published on the WEC website. You all have flyers on the desk in front of you, which will give you their website and give you details of the report. So this report has got some key messages. First of all, substantial cost reduction is expected. Secondly, quantifying the benefits of storage is actually quite difficult in methodological terms, in economic theory terms. We use principally this levelized cost of storage metric. It's very useful, but you need to understand exactly where it's come from and what it's used for. It depends upon the technology and on the location. That's fine. That applies to all generation technologies, the costs of all generation technologies. But critically, it also depends upon the application you're assuming for it. But that's not the only issue. Storage also has value, and we have attempted to look at the value issue. And in fact, I'm going to skip through this quite quickly because you've heard a lot of discussion already this afternoon about the value issue, potential values, improving reliability of renewables, security of supply, reserve capacity. We heard a lot about that from in the Terna situation. Possibility of price arbitrage, selling your power at times of peak prices, and also, very importantly, we're finding out, enabling deferral of grid investment. So the implications of this are that, as we've heard already this afternoon, there are still wide variations in energy storage costs for reasons that are understood and perhaps some reasons that are not yet fully understood. You need to look at value, not the cost. Establishing the cost is getting you part of the way to understanding the value, but the value is the important thing, not the cost. And for that, understanding the application is critical. And so, last slide here, our recommendations are that those who are considering storage, which might be renewables investors, it might be TSOs, could be owners of large demands, for example, have to understand that cost is not the only valuable variable to be considered. It's important to look at this through case studies. As I said before, the application is critical. You need to consider this through case studies that replicate very closely the intended use of the storage device. You will get very different results for different application cases. Grasping the value of storage is a hard issue. And the most important way to address this is by flexibility, markets for flexibility, or some other way of conceptualizing or achieving the value achieved for storage in conjunction with renewables and their benefits to the grid as well. And so that requires regulators and TSOs to work together to produce ways of getting good price signals to the investors in the storage. And I think the rest of the points you can read. I think I should just about finish just now in order to catch up time. So I'm very pleased to take any questions now or afterwards. Thank you.
Thank you very much, Mr. Gardner, and thank you for having given us the privilege of having this presentation on this brand new report just launched today. I think we are all very happy about it. Please have a seat over there, and we have a few minutes for questions, so I'd like you to, the micro, please, yes. And then here in the first row afterwards.
Thermal storage today is the most cost effective.
Could you start by introducing yourself? Thank you.
George Berberi from DC Pro Engineering. Thermal storage today is the most cost-effective storage technology in the world at a cost of $10 or 10 euro per megawatt, and is reducing construction cost by 15% and operating cost in chilled water application by 8%. We have 99% efficiency in heating. The best storage that you have today range between 80 to 93%. It's not in the menu of any of you because we don't have the thermal grids, the networks. Surprisingly, in Italy, no district energy. We have one in England, 3, 4 in France, 1 in Finland, 1 in Stockholm. Here, we are grasping in Dubai, we reach 20% district cooling, targeting 40%. Why, the question to any of you, in the world, why this is not on the menu? While we are integrating, we have a project in Oman, now we integrated 1 megawatt solar with 5 megawatt tri-generation, reaching 87% reduction and having storage on it. It's the world's most efficient project, most cost effective. It reduced national cost, but none of you in the world have it seriously on the menu. All of you are obsessed with centralized electricity and storage of electricity. 55% of energy use in Europe, in US, here is thermal. Here we have 50% cooling, 5% heating. In Europe, maybe 90% heating, 10% cooling, same in US. So if it is much easier and much cost-effective to store thermal energy, why is it not in the menu? Anyone can take it.
I suggest you take another question. Could you please plaster? No, here in the front, and then on the back. Thank you.
Thank you, Paula, and congratulations to the Commission for organizing this event. Pierre Bernard, Friends of the Supergrid. My question goes to Paul. You referred at the end, TSOs and the Commission should work together and regulators. And I may be wrong, but I think in Europe only one country has really allowed TSOs to invest also in storage, and that's Italy with some limits. And we see the positive results. Should we not go to a system where ownership of storage is put aside, and in order to facilitate investments, everybody should be allowed, whether it's generation, whether it's finance, whether it's TSOs and DSOs. Would that not help in the development of storage?
And we take the third question there, and then we go back to the panel.
Okay. Thank you. My name is Øyvind Johansen. I work in the Ministry of Petroleum and Energy in Norway. Thank you very much for a very interesting session. I think I have a comment or a question. Maybe it's Mr. Greter that is closest to answer. You mentioned that 99% of storage today is from pumped storage. But what about traditional hydropower reservoir? That storage, is there a technical issue, or maybe you could comment a little bit about that? Because in Norway we can store about 85 terawatt hours in our reservoirs. It can be tapped anytime, and we have about 30,000 megawatt capacity. And this is partly assisting our friends in Denmark so they can have this high wind penetration. And we are now looking into interconnectors with England and Germany who will take advantage of this mix. So maybe if you could also illustrate a little bit of what you think about traditional hydro with reservoirs. Thank you.
Thank you very much. Who wants to kickstart in answering? HubSpot? Yeah, thank you.
Yes. Hello. Thank you. Addressing the question directly addressed to me, it would certainly be very good for storage if the market was freed up to allow distribution network operators and transmission system operators to invest in storage as they saw fit. However, the regulators do not see their role as just to make conditions favorable for storage. So I'm sure that's the answer you would get if you talk to a regulator about it. They have bigger issues. However, I think I can speak from some experience in the UK that there is certainly a very strong pressure now to have some kind of relaxation for distribution network operators. It's widely seen that there are very good reasons for that, for distribution network operators to be able to have some kind of storage. So it may be that they're allowed to have some kind of investment in storage to a limited extent. And I think we will find out that as soon as that happens, there's substantial value released. And I'm fairly confident that at least at distribution level, the network operators will be allowed to have storage fairly quickly. If I could just leap in while I'm here on that thermal question, it's a very good point. However, in many countries, the value of energy is much higher if it's electricity than if it's heat or cooling. So thermal stores, if the end result is hot or cold, they're competing against actually much cheaper forms of energy than electricity. And I think that's probably the fundamental reason.
Thank you. Yes, I think it's your turn now. Thank you.
Do I have to switch?
No, you don't have to. You don't have to.
Okay. So thank you for your question. Of course, I know Norway and the potential what is there for storing. In general speaking, all the hydros are storage plants. So all the capacity you have is there. What I presented here today is only the pure pump storage plants. So I'm not focusing on Norway in this particular example.
Mm-hmm.
Is it the answer to your question?
Yeah.
Okay, thank you.
Thank you very much. Who would like to answer to our very first question or comment? Carolina.
I'm probably the only one that shouldn't be answering. I'm a transmission system operator. I move electrons. That's my job. I mean, I don't know what to do with heat. Sorry.
Okay, then we move to the second round of questions from the audience. Okay, very good. I think we come to an end. We are almost reaching the time we have to leave. I would like to thank all our speakers and also all participants to be here today. I think this is a very relevant subject that we are hearing more and more about. From our perspective, from the European Commission's perspective, storage will be one of the means to guarantee flexibility and facilitate greater integration of renewables into the grid. So it's an area that we will be looking very carefully in our next generation of legislation that will lead us to a market of that is the suitable market for 2030, based on 50%, at least 50% renewables electricity in the EU. I think we have had very good presentations of case studies, of demonstration projects, of relevant experiences across EU member states, but also the perspective in the Gulf. I think this was a very enriching discussion this afternoon, and please join me in greeting our panelists, our speakers for today's time and the contribution. Thank you very much.